Okay, so now that we know what vectors are, we're going to look at operations that are performed on vectors, and we're going to start with the sum of two vectors. Okay, so here's the following thing we're going to have to answer. So imagine I've got maybe a vector v that's like this, and another vector u, that's maybe like this. Okay, what's the sum of these two vectors? So we're going to have to define how we perform the sum. Okay, and the way this is done is that to add two vectors, we're going to take vector v, and we're going to so this is going to take us from here to here. And once we're here at the terminal point of vector v, we're going to place vector u so that its initial point is where the terminal point of v is. And this will create a path along v and u. And basically, we've now started here, and we end up here following this path. And joining these 2 points by a vector or line will create a new vector. So this is the vector we're going to call the sum of v and u. So we could call this vector w, and right now it's it's the same thing as v plus u. Okay, so in some way I've moved this vector u that's below here. Let me erase it, and I've placed it so that it's now starting where v ends, and that creates a new vector, which is the sum of v and u. Okay. All right. So here's a question for you that I'd like you to think about before moving on. So after that, pause the video and try to answer it. Is v plus u the same thing? Okay, following the way we constructed addition, is that the same thing as u plus v, or is u plus v a completely different vector? Okay. It may sound like a stupid question, but it's not. We know that for numbers, for instance, 2 plus 3 is the same as 3 plus 2. So we say that addition over real number commutes. Real numbers commutes, but the question is that also true with vectors? Because vectors are not numbers, so maybe they could obey a different kind of rule. So think about this for a second. Try to draw things. How about trying to draw what u plus v looks like, okay, and compare it to v plus u and try to answer the question. Okay, so if we want to illustrate or draw u plus v and compare it to v plus u, what we're going to do is, instead of starting our path with vector v, we're going to start it with vector u. So I'm going to put vector u here. And afterwards, where u ends, I'm going to start, I'm going to put the initial point of vector v where the terminal point of vector u is. So that means I'm going to put v here. It's not too hard to see that these two sides are parallel, these two sides are parallel. So really what this is, it may not show really well in the picture, but this is a parallelogram. So what you have here is a parallelogram. Okay, one side here, this is v, this is v. Okay, this is u here, this is u here. Okay, so we were creating a parallelogram, and the main diagonal of this parallelogram is the sum. Okay, and the sum is the same no matter whether you start with v or whether you start with u. So in fact, this statement is true here. So this is something we can you can write in your notes clearly, because this is something that's going to be very useful. Vectors, they behave like numbers. As far as addition is concerned, the addition of vectors is commutative. Okay, so here I could, I could write for this vector here, v plus u or u plus v. It's the exact same vector. All right. One thing that'd be nice to know also is how we can perform vector addition when we have the coordinates of the vectors. And for this, I'd like you to look at a picture in your book that I'm going to try to reproduce, but it's better if you look at the original picture in the book, because my drawing may not be as good. So you want to look at figure 3.1.13. In my book, that's on page 137. Okay, you want to look at the figure. The figure has two images, and you want to look at the image that's to your left. All right, so I did my best. As you can see, there's vector v in black that starts at the origin, and one thing you can see is that we've created a vector v with two components, v1 and v2. So we can write v as vector v1, v2 like this. Okay, and w in red also starts, we've placed it so that it starts at the origin, and you can see that it's got now two coordinates as well, w1 and w2. Those are the x and y coordinates of the terminal point of w, but that also corresponds to the coordinates of w, because w, just like v, starts at the origin. So this is w1, w2. So if we want to look at, we could look at v plus w plus v. Okay, so if we start with w and we add v, we're going to place v so that it lies, so that it starts where w ends. So you can see that it's right there. We've placed v right here. And in purple, you can see that with this right triangle that one side has length v1, the other side has length v2, because maybe let's illustrate. So this triangle here, that's the same as this one. Well, they don't look. It doesn't seem like they're the same triangles, because my picture is not perfect, but they both have sides v1 and v2. So when we're at the terminal point of w, we're going to move to the right by v1 and up by v2. So here's what's going to happen. So and then we're going to end up right there, and that point corresponds to the coordinates of v plus w, because it's a vector that starts at the origin, and it's the sum of w and v. So w and v, well, what is it going to be? So its x coordinate is going to be, we're going to move first forward by w1 and then by v1 to end up with so what I'm trying to say here is that the x coordinate of the sum of the two vectors is w1 plus v1. And the same is going to be true along the y coordinates, where we're going to first move up along w by w2, and then up by v2 along v. So we're going to end up with w2 plus v2. So the sum of two vectors is super easy. So if I have two vectors, I don't know, 3, 2 plus 7, 5, to add them up, all I need to do is add their components, component-wise. So I add 3 with 7 and 2 with 5, and I get the vector 10, 7. So to sum this up and summarize, what's interesting about what I've done here is that now I have 2 points of views for two point of views for the same operation. I've got a geometric point of view for addition, and I've got an algebraic point of view for addition. Okay, and sometimes it's going to be easier to look at things from a geometric point of view, sometimes from an algebraic point of view. And in this course, sometimes we're going to try to prove things. So sometimes it's easier with geometry, sometimes it's easier with algebra. And maybe I want to show you that algebra can allow us to prove something we've done already. Right? Remember, we've proven that v plus u is the same as u plus v using geometry. Because that new vector is just a diagonal of a parallelogram, right? We had done this before, so right. So this is the sum. So no matter if we start with v or with u, we're going to end up at the same place. But with algebra, it's also quite easy. So let's say I have two vectors, v, which is v1, v2, so two coordinates, and u is u1, u2. Let's try to show that u plus v is the same as v plus u. So if I look at v plus u, well, I know that all I need to do is add the components of the two vectors, like this, v2 plus u2. And what's interesting is that the components are real numbers. So right, this is a real number, this is a real number, and what I have to generate these numbers is that I'm adding also two real numbers. So v1 is a real number, v2 is a real number, u1 is a real number, u2 is a real number. So real numbers, they commute, right? So I can interchange the addition. So I can write u1 plus v1, and that's still the same thing as v1 plus u1 because I'm dealing with real numbers here. And this is u2 plus v2. So what I'm using here is commutativity of real numbers. The TVT of real numbers. This is what's happening between these two expressions. And then I can split it up again. This is u1 plus this is u1 u2 plus v1 v2, and that's with our definition of vector addition using algebra, right? That's using this up there, okay? So I'm basically going backwards, and this is just u plus v. So I've started with this, and I end up with this, and everything's equal. So the addition of two vectors is commutative again, and that's using a proof that relies on algebra. So for many of the things we're going to want to prove in this chapter, it's going to very often be easier to use algebra. So that took a while, but it's important to really understand how this works, and everything follows from this. So we're going to see that how we're going to take the difference between two vectors will rely on the sum, and how we add up three vectors will rely on the sum of two vectors. So everything's going to be a lot faster from now on. So in the next video, we're going to look at the difference between two vectors when we multiply a vector by a real number, and maybe also when we add three vectors together.